In section 5.3, we look at quantitative relationships based on chemical equations. Before we get going looking at chemical equations though, we're going to take a step backwards and look at some chemical formulas, and in particular we're going to look at the role that subscripts play in identifying the number of atoms of each type present in a formula unit of a substance. What I'm really getting at is if we look at a formula for a substance like water, what the formula is telling us is that in one molecule of water, there will be 2 atoms of hydrogen and 1 atom of oxygen. So if I was to ask a question such as, how many hydrogen atoms are there in 1,000 water molecules, it would be pretty obvious to recognize that we get 2 atoms of hydrogen for every 1 molecule of water. Therefore, if I have 1,000 water molecules, I'm going to have 2,000 atoms of hydrogen. So the subscripts in a chemical formula give us the number of each atom type present in one formula unit of that substance. So if I'm looking at Na2O here, it's telling me that in one formula unit of Na2O, there would be 2 sodium ions and 1 oxide ion. And given that information, you can calculate the amount of an element present given a certain amount of compound. The strategy that we're going to use to do these kinds of calculations is to use the formula subscripts to establish what we call ratios for each of the atom types that are present. For example, if we consider the compound N2O4, we can write the following ratios. We can say that there are 2 nitrogen atoms for every 1 unit or every 1 molecule of N2O4. Similarly, we could say that for every 1 molecule of N2O4, we get 2 nitrogen atoms. Those things are equivalent. We can do the same thing for oxygen. We can say that for every 4 oxygen atoms, we get 1 molecule of N2O4, or for every 1 N2O4 molecule, we get 4 oxygen atoms. So these are fractions that can function as conversion factors that allow us to convert from molecules of a compound to the number of a particular atom, or the other way around. So on the next slide, I'm going to illustrate this principle. Imagine I have 1.5 molecules of caffeine, and caffeine has a pretty horrendous formula. It contains 8 carbon atoms, 10 hydrogen atoms, 4 nitrogen atoms, and 2 oxygen atoms for every 1 molecule of caffeine. So if I have 1.5 molecules of caffeine, according to my formula, there are 8 carbon atoms for each 1 molecule. And so multiplying by that conversion factor here, or this conversion factor here, that tells me that I would have 12 carbon atoms. And I'm going to go through and do the same all the way through. And I'm just building my conversion factors from the formula subscripts. So if I've got 1.5 molecules of caffeine, I know that I will get 10 hydrogen atoms for every 1 molecule of caffeine. Therefore, I have 15 hydrogen atoms in my 1.5 molecules. Doing the same for nitrogen. 1.5 molecules of caffeine, and I get 4 nitrogen atoms for every 1 molecule. Therefore, I have 6 nitrogen atoms. So just multiplying my number of molecules by the appropriate conversion factor. Lastly, for oxygen, according to my formula, I have 2 oxygen atoms for every 1 molecule of caffeine. Therefore, if I have 1.5 molecules of caffeine, if I multiply that by 2 oxygen atoms over 1 molecule, that tells me that I'm going to have 3 oxygen atoms. So formula subscripts can be used to create conversion factors that allow us to convert between the number of molecules and the number of atoms of a given type, and vice versa. If we have a balanced equation, we can do some interesting calculations. One of the things that we can do is we can determine how much product can be formed from a given amount of reactant. So we can look at a pile of ingredients and go, okay, I can make this much of my desired product. So these types of calculations are referred to as stoichiometry calculations, which roughly means the measure of an element. These are chemical calculations regarding the amounts of things. So whenever you hear the word stoichiometry, what people are talking about is calculating the amounts of stuff. So we have this little example here of how we can perform calculations using the information contained in a balanced chemical equation. So our example reads, if 2 molecules of methane is reacted with O2, how many molecules of H2O are produced? So the key idea is to recognize that for every 1 methane that is reacted, I'm going to produce 2 water molecules. So if I am reacting 2 molecules of methane, and according to my balanced equation, I'm going to produce 2 molecules of H2O for every 1 molecule of methane reacted, you can see that I'm going to be making 4 molecules of H2O. And so rather than using a ratio of the components using formula subscripts, we're going to get our ratio of components using the coefficients that are in our balanced chemical equation. So we'll look at another one now. It says, if 3 atoms of iron is reacted with O2, how many formula units of Fe2O3 is produced? So this is our setup. Now what's important to recognize is for every 4 ions that we react, we're going to produce 2 Fe2O3s. So with that information in mind, the number of formula units of Fe2O3 produced can be calculated easily. We're going to be reacting 3 atoms of iron, and according to our balanced equation, we get 2 formula units of Fe2O3 for every 4 iron atoms that we react. So 3 times 2 on 4 tells me that I'm going to make 1.5 formula units of Fe2O3. So it's not too bad, right? It's pretty easy. We're just using the information contained within the coefficients of our balanced chemical equation to determine the amount of product that we're going to be producing. Of course, we can go the other way as well. So in this problem, we were asked, if I wanted to produce 5.8 formula units of Fe2O3, how many molecules of O2 would I need? So the key thing to recognize is that I will require 3 molecules of O2 to be reacted in order to produce 2 formula units of Fe2O3. So if 5.8 formula units of Fe2O3 are produced, and I know that 3 molecules of O2 are reacted for every 2 Fe2O3 produced, and then you can see that I can fairly promptly calculate the amount of oxygen that I need to produce my Fe2O3. So all I have to do is take 5.8 and multiply it by 3 on 2. So I need 8.7 molecules of O2. So I just took 5.8 and multiplied that by 3 over 2. Not too difficult. Here's another example from the book. It says start with this balanced chemical equation. It gives us our chemical equation there. It's in a slightly unusual form in that not all of the atoms are grouped together. And then it says verify that the equation is balanced. So the first thing that I'm going to do is start counting every atom type up. So we'll begin with potassium, then we'll do manganese, then we'll do oxygen, then carbon, and then hydrogen, and that covers every atom type. So there are 2 potassiums on the left, and we've got them all. Sorry, and there are 2 potassiums on the right, so that is confirmed. There are 2 manganeses on the left, and also 2 manganeses on the right. So that is confirmed. The oxygens are going to be a little bit more difficult. We have 2 times 4, that's 8 oxygens. And then out here we have another 4 oxygens. So 8 plus 4 gives me 12. On the right we have 2 times 2, that gives me 4 oxygens. Then we have 2 times 1, that gives me another 2. And then it's a little complicated here. We have 3 oxygens there, and then we have another 3 there. So 4 plus 3 plus 2, you guessed it, that equals 12. Now we're on to carbons. So we've got 3 carbons here, and then we've got another 3 here because we've got a 3 out the front there. And then over on this side, we've got 3 of these guys. So we've got 3 carbons there, then another 3 carbons there. So we have 6 carbons on each side. Now, having done all of that work, it seems unlikely that the hydrogens don't balance, but we'll find out in a second. Just erasing some of these things. My eraser is not very good, you might have noticed that. But what we're going to do now is we're going to add up all of our hydrogens. So we've got 3 times 2, so that's 6 for those guys, and then 3 times 2 again, so that's another 6, and then 4 times 2, that's 8. So that's all of our left-hand side, so 6 plus 6 is 12, plus 8 gives me 20. So on the other side, we got 3 times 1 there, so that's 3, and then 3 times 2 there, so that's 6, and then 3 times 2 again, so that's another 6, and then 3 times 1, so that's 3, and then 2 times 1, so that's 2. So 3 plus 6 is 9, plus another 6 is 15, plus 3 is 18, plus 2 is 20. So it looks like everything is balanced. Manganese is balanced, oxygen is balanced, carbon is balanced, hydrogen is balanced, potassium is balanced. So finally we're asked to give 2 ratios that give the relationship between KMnO4 and CH2CH2. So let's identify those guys, CH2CH2 and KMnO4. And we can see pretty easily what it is. We get 2 KMnO4 for every 3 CH2CH2, Or our second conversion factor would be 3 CH2 CH2s for every 2 KMnO4. So there are two ratios relating those things to each other. Okay, so that concludes section 5.3, quantitative relationships based on chemical equations.